So the last major class of reactions that we are going to learn about this semester involves a carbon-carbon bond formation that proceeds through an intermediate known as an enolate. Now an enolate is simply a deprotonated form of the enol. So if we think of an enol as just being a hydroxyalkene, so here is an enol, right? En meaning alkene, ol meaning alcohol. If we take a base and deprotonate that enol, we get a structure known as an enolate. Right, so this is an enolate. Enols, as we remember from last semester, they are in equilibrium with their keto form, and so we can draw that. This involves a tautomerization, so if we put that hydrogen right there, this is the keto form of the enol. And we say in most cases the the keto form is favored because you have a carbon-oxygen double bond and a carbon-hydrogen single bond. So this is 410 kilojoules per mole, and the carbon-oxygen is 730 kilojoules per mole. Whereas in the enol form, we have a carbon-carbon double bond and an oxygen-hydrogen single bond. So this is 425 kilojoules per mole, and the carbon-carbon is 610. Okay, and so the sum of those bond enthalpies tells you that the keto form is a little bit more stable. But we can draw the enol form in its enolate form by treating it with base, just like we can draw the keto form in its enolate form by treating it with base. And so in the case here, we're going to get deprotonation of that keto form to give us a negative charge on carbon. And this demonstrates that these two enolate forms are indeed resonance forms of one another. Okay, so we can draw a resonance arrow in between them. And so in the case of the enol to keto tautomerization, this is a true equilibrium. Right, this is the tautomerization. Right, but in the case of the deprotonated enolates, this is a different type of arrow. This is a series of resonance forms. Now, enolates themselves have these resonance structures that place the negative charge on the oxygen and the carbon, and this type of arrangement is really an allele-like system. So it has allele-like reactivity. And we'll get to this in the next lecture when we talk about the molecular orbital description of the enolate. Now, this equilibrium between the keto and the enol forms is not necessarily rapidly established. There could be some barrier, but the overall movement of a proton through the pi system, that's known as a tautomerization. Right, the keto form we said was normally favored because the CO double bond is stronger. And you might promote tautomerization to the enol form by reducing the amount of electron density on the carbonyl. Right, so in order to promote enol formation, you can do the following. You can reduce the amount of electron density on the carbonyl. And so why would you do this? This would allow for better overlap between the sigma CH and the pi star CO, right? And so the whole idea is you want to take that sigma CH and delocalize it into the pi star CO. And if this thing is lower because you don't have a whole lot of electron density on it, then there will be a much better chance that that type of interaction will occur. So more signal donation will result, more enol will be formed, and the proton that is moving will become more acidic. Another way of saying this is as follows. As the electron deficiency of the carbonyl builds up, signal donation donation is greater and more enol forms. So I'll write that down. As electron deficiency builds up, sigma donation is greater and more enol forms. And remember, we're forming this overlap between the sigma CH and the pi star CO. And so we could draw this in a diagram like this. So this is for acetone. Remember that we have the sigma CHs are overlapping into the pi star CO. So let's draw the pi star CO, something that looks like this. And then we have the sigma CHs right here and here, and then we of course have 6 of them, and we get this overlap happening to give us the enol formation. Now I made reference to the fact that things that form enols more are going to be more acidic. And so let's talk a little bit about the correlation between enol formation and acidity. Right, so the pKa of the enolizable proton correlates with greater stabilization of the negative charge in the conjugate base. The pKa of the enolizable proton correlates with greater stabilization of the negative charge in the conjugate base. All right, so let's consider the trend below. And so we've got that system. We've got this system. So we've got an amide, we've got an ester. Let's draw a ketone. Let's draw the corresponding aldehyde. And then let's draw a couple that have 2 carbonyls. Okay, and so in this particular instance, we can draw a correlation to the pKa. So what is the pKa of each of these protons? Well, the pKa of the proton here for the amide is about 30. For the ester, it's 25. For the ketone, it's 20. For the aldehyde, it's 18. For the diester, the dicarbonyl, that's 13. The case where we have an ester on one side and a ketone on the other side is 11, and then 2 ketones is 9. And so we can draw a correlation here where we're saying that the more enol you get is going to be towards the right. Right, so more enol is over here. And the reason that this happens is because you have greater stabilization of the negative charge in the conjugate base. So if you were to deprotonate each of those protons, the negative charge is better stabilized in the structures on the right than they are on the structures on the left. And that's because in the structures on the left, those structures have more electron density on them. So they're not going to be as electron deficient. Now the cutoff for keto with their enol tautomerization is roughly a pKa of about 20. 18 to 20. Okay, In 1,3-dicarbonyl compounds that we have on the right-hand side, the central atom's pK is quite low due to the double resonance delocalization that could occur. But in the cases on the right, on the left, we don't have that double resonance, and so it's often the case that those exist almost exclusively in the keto form. So let's take a look at how this might manifest itself in some KEQ values. Okay, so let's take a look at the KEQ value for the keto to enol tautomerization for acetaldehyde. Let's compare that to the keto to enol tautomerization for acetone. Okay, so the pKa, or the KEQ, for the first case is 5.9 times 10 to the minus 7. In the second case, it's 4.6 times 10 to the minus 9. So this tells us that the aldehyde is roughly 100 times more likely to form the enol than the acetone is. All right, and so in this particular instance, aldehydes, as we know, are more electron deficient. Right? More electron deficient than ketones. So more enol is formed. Remember in our discussion of the reactivity series and carbonyl chemistry, we said that the inclusion of that hydrogen there prevents sigma donation from happening into the pi star, and so this species is very, very electrophilic. Okay, let's compare number 1 to number 3, in which we have more substitution. And so let's say we've got this aldehyde, and we're forming this enol. All right, so we're comparing number 1 to number 3. In this case, the KEQ is 1.0 times 10 to the minus 4. Now, why is this, roughly 1,000 times more stable in the case of the enol than the acetaldehyde is? Well, this is because you have a more highly substituted hydroxyalkene. Remember from our discussion of alkene chemistry last semester, more highly substituted alkenes are more stable. And so this will give a more enol. We can extend this type of analogy to the keto form. The ketone, excuse me. All right, so in this case, we've got a KEQ of 3.0 times 10 to the minus 8th. And so if you're comparing number 2 to number 4, in which you have more substitution, a more highly substituted hydroxyalkene in number 4, you're going to be you're going to have more enol, and so it's roughly 10 times more enol in this case. Another factor that's important here is aromaticity, and so let's draw a different compound. Let's draw this one. Okay, and the KEQ here, if we draw the enol form for this, the KEQ here is 17. Okay, and so the reason for this is that you've got a sort of quasi-aromatic system. So 4n plus 2 here is 14 pi electrons. Which is aromatic. All right, you can draw a resonance form for this enol in which you're going to place the negative charge on that central carbon atom. And when you do that, you'll have a aromatic system. Right? You'll have 14 pi electrons. Okay, a couple more examples of keto to enol tautomerization. Let's talk about the double carbonyls. Right, so let's say we have this dimethyl ester. Right, if we were to form the enols for this, we would get actually two different enols. One enol would be this one. But we would also have an enol that looks like this. And in this particular instance, you cannot distinguish between these two. Okay. The reason you can't distinguish between these two is because it's one symmetric, but also you kind of have a 4n plus 2 pi electron like system. And so what you really have is a system in which you've got a 4 pi ring of electrons, which is highly delocalized. Right, so you've got a system that looks like that. Because you have this intramolecular hydrogen bond, you can stabilize the enol. And really the two different enol forms are exactly the same as one another, and so you get this intramolecular hydrogen bond no matter what. Now what happens if it's not symmetrical? And so let's look at the following. And so if we were to take this keto ester and draw the two enols that would form, we would get one that looks like this. And there's that intramolecular hydrogen bond. But we also get one that looks like this, with this intramolecular hydrogen bond. And so the question here is which one is favored? And it turns out that this one is favored, right? Because the non-bonding pair of electrons on oxygen in the ester are more basic. Right, so because you can take these electrons and delocalize them into the oxygen atom, they're going to be more basic and they're going to want to interact with that hydrogen right there a little bit more. And so that's why that enol form is more favorable than the other enol form. Another interesting consequence of this comes when we think about this diketone. Right, so the KEQ here is equal to 6. And so we would get this series of enols, right, with the individual intramolecular hydrogen bonds. It turns out that in this particular case, the NMR gives one peak, right, for the methyl groups. Because this molecule is symmetrical and you have a 50-50 mixture of each of those enol forms, the methyl groups on this one are exactly the same as the methyl groups on this one. And so they'll show up as a 6-hydrogen singlet instead of individual 3-hydrogen singlets. All right, so let's switch gears a little bit and talk about how we might promote enolization. And you can do this under both acidic conditions and basic conditions. Okay, so let's talk about acidic conditions first. Let's say we have this ketone, and we want to enolize it to this enol. And I'm just going to draw a squiggly line because, of course, we have stereoisomers. And I'm doing this under acidic conditions, so I'm just going to label this as BH+, right? Recognizing that here you've got a labile proton. And so what you can do is you can take the non-bonding pair of electrons on the oxygen and protonate it from that BH+. And so you're going to get a protonated carbonyl as such. And then what happens is that you've got a really, really low LUMO, right? So this makes it even more acidic, all right, and promoting enolization. And so the base can come along and do a deprotonation followed by formation of the alkene. And so what you get is a series of enols in which you've got one enol is the trans enol and the other enol is the cis enol. And it turns out in this case, this one is favored because the R groups here are on opposite sides. Now, how might that happen under basic conditions? Okay, so let's have the same ketone, but this time we're going to have this under basic conditions. Let's just say it's something like hydroxide. It doesn't really matter what it is. The first thing that happens is the base is going to deprotonate, and you're going to place the electrons up onto the carbon, and you're going to have a resonance form in which the negative charge exists on carbon. Right? This can undergo resonance delocalization to give you the negative charge on oxygen. And then the base that deprotonated in the beginning will become BH+, and that can be deprotonated by the oxygen, right, to give you the enol. And again, as a mixture of two stereoisomers. Now remember, in order for enolization to happen, you have to have proper orbital overlap between the sigma CH and the pi star. And so an important caveat here is that we need to make sure that we follow proper orbital alignment. And so the example here is the following. So let's say we have that ketone. This is a bridged bicyclic system. We could draw an equilibrium to the enol form of that one, and it would look like this, in which we've got this enol forming on the apex of that bridged bicyclic system. Now, why does this not happen? Well, the reason this doesn't happen is because the two orbitals are orthogonal to one another. Right? The sigma CH bond is actually perpendicular to the pi star CO. And so because of this, there's no sigma donation, and you don't get any enol forming. Okay? This is another way of stating Brett's rule. Remember, Brett's rule states that you can't have an alkene at a bridgehead carbon, And so an extension of that is you can't have an enol in bridge bicyclic systems. And so again, you have to have proper orbital alignment between the sigma CH and the pi star CO in order for this to occur. In this particular instance, they're perpendicular to one another. Okay, so we now have this, this idea of enolization or keto to enol tautomerization. And so what might be some of the consequences of this keto to enol tautomerization? Why does it matter that these things happen? Well, I'm going to show you 4 different reasons why it matters. The first one is called alpha epimerization. And what is alpha epimerization? Alpha epimerization is the stereochemical equilibration of a stereogenic center. And this can happen under acidic conditions or basic conditions. Okay, so let's say we have this species right here. This is chiral. And so let's say we take this and throw it in acid. What might happen? Well, what might happen is you might get an epimerization to occur, or a tautomerization to occur. And so we get the ketone to protonate, right? That gives us a protonated alkene. Excuse me, a protonated carbonyl, which then undergoes a keto to enol tautomerization to give us this species. This species is now achiral. And so we've lost our stereogenic center. And it turns out that we can't get it back. And so if we were to then reform the keto form, either by protonating from the top face or protonating from the bottom face, right, so let's say I protonate from the bottom here and the top here. If I protonate from the top face, right, I'm going to get a species that looks like this. And if I protonate from the bottom face, I'm going to get a species that looks like this. And of course, we can undergo basic deprotonation to reveal now our 2 ketones which are enantiomers of one another. And so what we have is a racemic mixture. And this happened all because we took a chiral ketone, which had the ability to undergo a keto to enol tautomerization, and we threw it in acid. Right, so this is acidic conditions. What might happen if we were to do this under basic conditions? Let's do the following example. Let's say we have this starting material. And this time, we're going to throw it in basic conditions. We'll throw this compound in base. All right, what might happen here? Well, I'm going to draw this in its sort of cis-like form. And it's going to undergo deprotonation here with terbutoxide. And so I've got deprotonation here, and then formation of the enolate. And so the enolate is, of course, going to look like this. And again, we've lost our chiral center right here. And so now that center is completely racemic, just that particular carbon. And so when it reprotonates with terbutanol, what might happen is it's going to reprotonate to give you the more stable diastereomer. And we all know that transdecalins are much more stable than a cisdecalin. And so when it protonates, it almost exclusively protonates from the front face to give you the transdecalin. Right, so attack from the top face to give you that transdecalin. And again, this is all a consequence of this idea of alpha epimerization. If you have a stereocenter, alpha to a carbonyl, under acidic or basic conditions, you might lose the stereocenter because of the intermediacy of an achiral species. Okay, the second consequence of keto to enol tautomerization is the isomerization of non-conjugated enones into conjugated ones. Okay, so let's say we have the following molecule. And let's say we throw this into acidic conditions. What we're going to do is we're going to equilibrate this, or isomerize this, into a different structure. Okay, so we started with a system in which the double bond and the carbonyl were non-conjugated. We call this a skipped alkene because we have an intermediate sp3 hybridized carbon. But in the product structure, we have a conjugated system. Okay, so how does this work? How do we do this? Well, under acidic conditions, of course, we can protonate the carbonyl. And I'm just going to abbreviate this for now. Okay, once that carbonyl has been protonated, right, we can have some base, labeled just BH+. Some base can come along and do a deprotonation to form an enol. And this enol looks like this. And so what can happen next is you can get the enol to reprotonate, but this time it will reprotonate at the terminal position. And so again, you're going to get a proton there. And you've established now your conjugation. And of course, the base can come along and neutralize this to give you now your free conjugated enone. Right, so isomerization of non-conjugated enones into conjugated enones can occur. And again, this can happen under acidic conditions, or it can happen under basic conditions by a very similar mechanism. Right, the third thing that's a consequence of keto to enol tautomerization is the exchange of alpha protons for deuterium. Okay, so we know that deuterium is just a proton that has an extra neutron in its nucleus. And so if we were to take this 1,3 diketone and treat it in the presence of D2O, well, the first thing that might happen is you might get an enol to form. So let's say we get this enol to form. What happens next is that the deuterium will become incorporated. And so you will exchange the proton that's on the oxygen, which is pretty acidic, pretty labile. You exchange that proton for a deuterium. And so you're going to replace that, that hydrogen with a deuterium. This can then tautomerize again to give you the deuterium now on the carbon. You can reestablish again this equilibrium. It tautomerizes to give you another hydrogen on that oxygen. It will again be replaced by D2O. And you can again tautomerize to the diketone. But this time the diketone now has 2 deuterium incorporated. Right, so essentially what's happening here is that in the proton NMR, the signal for the CH2 will disappear, right, in the presence of D2O. And again, this happens because of this intermediacy of the enol and the ability for deuterium to readily exchange with hydrogen. Next consequence of keto to enol tautomerization is actually a quite large one. And this involves the ability of enols to undergo electrophilic addition. So enols are electron-rich alkenes. And we know that alkenes undergo electrophilic addition reactions, and so enols can also undergo electrophilic addition reactions. Okay, so enols and enolates are nucleophiles. They're nucleophiles that react through the pi bond, right? And so we're going to take, let's say, this enol, and we're going to react it with some electrophile, let's say E+. Right? So what happens here is it reacts through the pi bond, and so the electrons on oxygen are going to increase the HOMO, and it reacts through the pi bond, and it's going to give us a new carbon electrophile bond. And then, of course, we can get a deprotonation to occur to give us the new carbon electrophile bond. Now, notice the regiochemistry of this reactions, of this sequence. We took the more delta minus carbon here and reacted it with the electrophile. So the oxygen lone pairs increase the nucleophilicity of the alkene, right? It increases the HOMO, right, the pi CC. But that pi CC is more delta minus, of course, at that terminal carbon because of the resonance form for this species. Okay, so what's an example of this? An example of this is the reaction known as the alpha halogenation of ketones. Okay, so alpha halogenation of ketones can be performed under acidic conditions or it can be performed under basic conditions, but the products are actually quite different. Right, so let's see what happens under acidic conditions first. All right, let's say we have this ketone, and we're going to react this ketone with acetic acid in the presence of bromine. Okay. So the first thing that happens, all right, is that you're going to get a protonation of the ketone with acetic acid. So we're going to protonate that ketone to give us a protonated cyclohexanone. So the pKa here is about 20. The pKa here is about -7. So very, very acidic. And so that means we can deprotonate, right, with the acetate anion to give us an enol. Now this enol, we can think of this enol as being an electron-rich alkene. We know that alkenes react with bromine. The way this is going to react is not via a bromonium ion, but it's going to be sort of an electrophilic addition, where you've got now a new carbon-bromine bond. And then we've got bromide can come back and deprotonate. And so the product of this reaction is going to be your alpha bromo ketone. All right, so this is the product of this reaction. Now, why can't this just react again? Let's think about what might have to happen in order for this to react again. In order for this to react again, the first step of the reaction would be we would have to protonate the alkene, or protonate the carbonyl. And this step is really, really slow. And it's really slow because the bromine is pulling electron density, all right, from the carbonyl. The non-bonding pair of electrons on oxygen are less basic because the bromine's there. And so it's less readily able to pick up a proton. Right, so bromine's electronegative and it's pulling electron density away from the carbonyl inductively, making the carbonyl lone pairs less basic and less likely to protonate and form a second, or perform a second bromination. In other words, the monobrominated product is less reactive than the starting material, so the reaction stops at the monobromination. Now, as you might suspect, this is not the case under basic conditions. So let's think about what happened under basic conditions. Okay, so let's take this ketone, and this time we're going to react it with bromine in the presence of base, sodium hydroxide. All right, so the first thing that happens here is we get a a deprotonation. So hydroxide comes along, does the deprotonation, and we get an enolate. So we can draw out the enolate as this, or probably what's more likely is to draw in its resonance form where it has the negative charge on the electronegative atom, oxygen. Right? Then, of course, it reacts with bromine to give you the alpha brominated product. And so we now have a new alpha brominated product. But here's where we differ under acidic conditions versus basic conditions. Under basic conditions, this is actually more reactive. Because under basic conditions now, your CH is more acidic than the original starter material. So under basic conditions, you're not just going to stop at the monobrominated product. Your hydroxide is going to immediately deprotonate again. And so it's going to deprotonate, form an enolate, and then react with another equivalent of bromine to give you now the dibrominated product. So under these conditions, the product of the monobromination is more reactive than the starter material. The alpha CH is more acidic because, again, your bromine is inductively withdrawing. And so because of that, the reaction continues. So a second and maybe even a third bromination can occur, and it's very difficult to stop this reaction. So let's talk about one more type of reaction under basic conditions, and that's the reaction in which you have a methyl ketone. So let's say instead of the ketone that had an alpha group, we had a ketone that had a methyl group. Right. So let's again react this with sodium hydroxide and bromine. Right. First thing that's going to happen is we're going to get sodium hydroxide to form the enolate. That then is going to react with bromine to give you the monobrominated product. And again, that is more acidic. That proton is more acidic than the starter material, so hydroxide can come along and deprotonate again to give you the enolate. That enolate is then going to react with another equivalent of bromine to give you the di-substituted, dibrominated product. But again, that hydrogen is now even more acidic. And so hydroxide can come along and form an enolate once more. And now you can get a third bromination. And so now you have this tribromo ketone. And so this tribromo ketone is actually not the product of this reaction. Because what happens next is it reacts with another equivalent of hydroxide. But the hydroxide this time is not going to do a deprotonation. What it is instead going to do is it's going to attack the carbonyl. If you think about it, these bromines are pulling electron density towards them. They're really electronegative. And so that's going to make that carbonyl really electropositive. So it's going to want to perform a nucleophilic acyl substitution reaction. Okay, so if we get hydroxide to attack the carbonyl, what do we get? We get O minus hydroxide and then our tribromomethyl group. What happens next is that you get collapse of that tetrahedral intermediate with loss of the leaving group. And this is the only time in which we get loss of a carbanion. Because what happens is the carbanion, you generate a carboxylic acid plus the carbanion that has the 3 bromine on it, tribromomethane. And because of the electron withdrawing ability of the bromines, that's going to make that carbon pretty stabilized. Right? It's a good leaving group. And so the negative charge is immediately going to deprotonate that carboxylic acid, right? Because any base can deprotonate carboxylic acids to give us a carboxylate plus CHBr3, and we call this bromoform. It has a structure very similar to chloroform, CHCl3. And now this is a byproduct of the reaction. We've got this carboxylate, but this carboxylate can undergo protonation in a workup step, and it's a good way of making carboxylic acids. All right, and so if you take a ketone and react it with sodium hydroxide in the presence of bromine, and that ketone is a methyl ketone, it's a good way of making carboxylic acids. You get tribromination via the electrophilic addition mechanism through the intermediacy of that enolate, but then the additional equivalent of hydroxide can attack the carbonyl and undergo a nucleophilic acyl substitution to give you your carboxylic acid product.